Hello dear students. Today we are going to learn network flow, an important topic in graph theory and optimization. A network flow problem asks, given a network with limited capacities, what is the maximum amount that can move from a source to a destination? This concept is widely used in internet routing, transportation systems, water distribution, supply chains, and social networks. So the network flow. So real world idea of network flow. So imagine a huge water tank continuously supplies water. Several pipes connect the source to a destination tank. Every pipe can carry only a limited amount of water. The question is, what is the maximum amount of water that can reach the destination? So this is the real life example. With parallel to this social media example, water is the messages, pipes or user connections, capacity is users available time and attention. Each user can only send a limited number of messages. So we ask, what is the maximum number of messages that the entire network can handle? This is exactly a network flow problem. So that the flow network, a flow network is represented as G of V, E, C, where V is the vertices, E is the edges and C is the capacities. So that the important rule is capacity C of U, V greater than or equal to 0. So every edge has a non-negative capacity. Example, a pipe can carry 5 units, 10 units, 20 units, but never a negative amount. Source is the starting point. It has unlimited supply. And sink of T. Sink is the final destination. Everything eventually flows here. And then directed flow. Flow moves only in the specified direction. If U, V belongs to E, then V, U not belongs to E. So think of it as one-way street. So see this graph as the example, there is only one direction in the flow. And the next one is flow. So capacity only tells us the maximum allowed flow. Actual flow is represented by F of U, V. Capacity constraint, which means flow cannot exceed capacity. 0 less than or equal to F of U, V less than or equal to C of U, V. So capacity equal to 10. So the possible flows are 4, 8 and 10. We cannot exceed the 10. And then conservation. Every node except the source and sink, incoming flow equal to outgoing flow. No flow is low cost inside the network. For example, if a node receives 5 plus 4 equal to 9 units, it must send out 9 units as well. These are the constraints. So the next is sample flow network. Edge labels are shown as F by C, where F is the current flow, C is the capacity. For example, 3 by 5, 8 by 13, 11 by 14. Here 11 is the current flow and 14 is the capacity. And then flow quantity. So flow quantity means total amount of flow moving through the network. It can be calculated in two ways. Method 1. Outgoing flow from source minus incoming flow to source. The second method, incoming flow to sink minus outgoing flow from sink. So both methods give exactly the same result. And then what is the flow value? In this example, from source 11 plus 8 equal to 19 units leave. At sink 4 plus 15 equal to 19 and units arrive. Therefore, flow value equal to 19. This means the network is currently transporting 19 units. Next, Ford-Fulkerson algorithm. So this is the flow value 19. Next one is Fulkerson algorithm. This is the famous algorithm used to find maximum flow. Basic idea is step 1. Find a path from source to sink that still has available capacity. And the next step, push as much flow as possible through that path. Step 3, repeat. Step 4, stop when no more paths exist. At this point, the maximum flow has been found. Next one is residual network. After sending flow, we need to know how much capacity is still available. For this, we build a new graph called the residual graph. So residual capacity tells us remaining capacity equal to capacity minus flow. The residual network helps us decide where more flow can go, whether some flow should be rerouted. An intuition of residual network, suppose capacity equal to 10, current flow equal to 4, so residual capacity is 10 minus 4 equal to 6. It means 6 more units can still be sent. And then reverse edge. Residual networks introduce something interesting. Suppose we already sent 4 units, the residual graph allows us to send those 4 units backward. Why? Because we might later realize there is a better route. Backward edges help us undo or cancel some previous decision. And then this is the residual network example. So the left graph is the left graph is original graph, right graph is the residual graph, contains remaining forward capacity, reverse capacity for cancelling flow. So edges with zero residual capacity are hidden because they are useless. So the next one is augmentation and augmenting path. So the residual capacity indicates how much more flow we can send. So forward edge, residual value means how much extra flow can still be added. Backward edge, how much previously sent flow can be cancelled. Using these residual capacities, we can improve the solution. This improvement process is called the augmentation. So the next one is augmenting path. Any path from source to sink in the residual graph. If such a path exists, we can increase the total flow. So the next one is weak link. The amount of extra flow we can push is determined by minimum of capacities along path. The smallest capacity act as the bottleneck. This edge is called the weak link. So the path capacity is 10, 7, 3, 8. Maximum additional flow is 3 because 3 is the smallest value. Is how do we augment? Suppose the augmenting path can carry one additional unit, then forward edge increase flow by 1. Reverse edge decrease residual capacity accordingly. After updating all edges on the path, original flow increases, residual graph changes. The slide's example increases the flow quantity to 1 unit from the previous state. In this graph, the flow quantity increases to 1 unit from the previous state. So the flow quantity is 1. So the augmenting example. This slide demonstrates several augmentation steps. The step is step 1, finding an augment path. Step 2, identify the weak link. Next, push flow equal to the weak link. Then update residual graph. Then repeat. So next one is 4-5% algorithm. So the complete procedure is start with the flow equal to 0, then build the residual graph, find an augmenting path from source to sink. At the next, find the bottleneck, which is the weak link, increase flow by bottleneck value, update residual capacities, and repeat until no augmenting path exists. So this is the network flow and then residual graph algorithms. So thank you students.